Fisch has the background in energy technology from University of Stuttgart from Germany and has many years of experience in energy in building and solar technology. And now he's a managing director for ETS Plan. He was a founding member of Solar, the energy company. And now he's the head of the IGS, Institute of IGS from Technical University of Braunschweig in Germany. And he's also the founding member of Energy Design. Also EGS Plan International, where he works worldwide in China, Middle East, as well as in Thailand. And also Professor Fisch have received numerous awards, such as BMWI Award for Energy Efficient School in 2014, awards for Exemplary Good Buildings, Goldener Award, German Solar Award, and also many kinds of publications. Okay, so perhaps Professor Fisch could maybe elaborate more from your side, Professor Fisch. And so now it's the time. I would like everybody to please welcome Professor Norbert Fisch for his lecture.
You don't hear me? No? Maybe this is the reason that this noise coming from this air conditioning system. This is one of the segments we speak about green buildings to avoid noise in the lecture room. It's one. So first of all, I would like to thank for this invitation and especially all the people who have organized this event so that you'll be here. And let me say it this way. I prepare a little bit the lesson, yes, right. The professor speaks normally about from the students about lessons, and maybe if it's sometimes too boring, I will skip it. You will see. I would like to start first with one slide only. We saw the small German country in the middle of Europe. We are nearly in Europe 450 million people. In Germany we have only 80 million. And our capital is Berlin. Maybe you know that, but maybe you don't know where Stuttgart is. It's my hometown. And Stuttgart is south of Germany, and the university I work in is more closer to Berlin, like to Stuttgart. So every week I go in by high-speed train from Stuttgart to university. It's nearly 500 kilometers. So Germany is small, not like as you see in Thailand. We are much bigger in distance. And when you see, we are a similar population. Maybe you are not so dense like in Germany. You have, let's say, more land and less people. So Thailand is nice to live. You have a lot of space. Of course, you have a different climate. And when I speak about some approaches, then of course we know that we could not adopt all our solutions, what we have learned in our country about buildings, about all products. We could not only shift to Thailand, because you have total different mentality, total social background, you have total different climate, of course. So sometimes it's not so, every system could not adopt in both countries. But what is interesting, and at the moment Professor Pandit is also in our city, in our university. I'm here and Professor Pandit is there, so it's nice to communicate this way also. And one thing what Professor Pandit would like to also check is that professors like I have two legs, as normal people have legs, two legs. One leg is on the university and the other leg is on my, let's say, private business, it's consulting business. Because I sometimes tell professors in the United States how you can teach people to build buildings when you not build buildings. I mean, it's an absolutely request. If you're a professor in architecture and in engineering, you have to be your own office. You have to be your own design office that you can tell the people how it's really done, how it's really doing, because you could not read in books how you build a building. Maybe mathematics and physics you can read in books, but to build buildings you have to do it. If you not do it, it will speak about. This is the reason. This is these companies. Acha mentioned it. This is my heart, and maybe this is a brain. Like maybe this way. My heart is on the university, but my brain is also in the business outside of the university. And we are nearly 100 people, and these 100 people working in these different fields, different aspects of, let's say, advanced buildings. We started in 2013 with a cooperation here with Professor Ach. We found a good partner. He's an architect, we're an engineer, so it is a good way how to collaborate. Engineers and architects should work close together. And this is also what I like to mention on this university. We have one of the first called Master Sustainable Design. It's the first master in Germany where architects and engineers go in the same classroom, doing the same curriculum. The architects more focus on design, and engineers focus more on engineering tasks. It's the first master where you have the same people in the same classroom from architecture and engineering. 4 semesters means 2 years, and we established this 3 years ago. And it's now really successful, and maybe we can adopt that also here in Bangkok. It's running. Not so easy. I know this discussion about architect and engineers. There's always a big discussion how we should do same master for architect and engineering. This is a big discussion. But if practice is happening, we speak about later on integral planning, and integral planning is only when you work together. And what we're teaching is we have a classroom for architect and we have a classroom for engineers. It's not crazy, because in the practice we work perfect together, and in the universities we separate the people. This is not what we're thinking is the future. So this is the team, and what we offer is, of course, concepts for building and cities. In the past, we looked mostly on buildings, but in the fewer days, the last years, we're looking more on cities, because the goal of solution is not a building, the city is a city part of a city. The city is consisting of districts, so we are looking more and more in the last years on energy concept of cities. Building simulation, building physics, and HVAC design, this is our, let's say, core disciplines, what we're doing in our practical work in EGS plan, Stuttgart EGS plan, International Gate Bank. So why we have to change our, let's say, our thinking, and why we have to change our approaches for design of cities and buildings. There's a lot of arguments. You know this urbanization topic. We know also maybe in China we have a big problem with demographic change. For looking to Japan, the society of Japan is really a big problem of elderly people. A huge big problem, and we architects and engineers will have to react on houses. Now a lot of Japanese coming to Thailand, but we have to react on this demographic change in the society. It is one of the big challenges. It's not only energy and CO2. There's a lot of other big problems what we are rising in our society, in resources, in internationalization, and so on. This is some of the key points where we have to need to change our let's say, planning approach for the future. So life cycle analysis. I know that this is in the most of the cases happen also in Germany, by the way. And also when you're going to Dubai, when you're going to Saudi Arabia, and you're going to Thailand. What are the people thinking? The people thinking, I have an investment, and this investment has to come very soon back. One pocket of money, tomorrow I have 2 pockets of money. This is what also the Germans thinking, most of the investors. And I think also in Thailand. When you have an investor, he don't think on the life cycle of the building, he's thinking on the just in the moment. And this is what we're understanding on the life cycle analysis is that we have the building. This is the European Central Bank. Later on I come to this building because we were involved in this building. In the beginning we have got a concept, we have a design phase, we have a construction phase, and then normally when the construction is finished we hand over the building to the client and finish. But the longest time the building is surviving, is living, is the time where the building is in operation. This is the time where the building is, let's say, during 20 years, 50 years, 100 years, the building is in operation, is in use. And so if you're not looking at the whole cycle, if you look only on the concept or on the first design, then you cannot learn. The most things we learn, by the way, is when we're looking on the real projects in the practice. The most thing I learned in my life was not in the books. It was when we're looking on real building. How the building are really function, how the building are really react on our actions. I would not like to say that you should forget your study, but the main experience what you're doing is in the practice. And so to monitor the building and to evaluate the building, how it's really performed. A lot of people make simulation concepts, but in reality, most of the simulations are not showing the true work. You can make nice pictures, nice colored pictures, CFT simulation, but what is in the reality? When you measure, you will see what is the reality. So what is with the cost? You see this figure here that in the beginning, this shows you that during the whole phase of design and construction, maybe only 20% of the total cost is in the first phase, means design and construction. Over the whole life, we have 80% or 85% is the running cost, and the investment cost, means the capital cost, is maybe 20%, and the total cost of building over the lifetime is 80%. And when we're doing design, when we're doing concepts and design, the most influence of this cost is at the beginning. So the impact, when we engineers and architects and starting in this integral approach, the biggest impact is at the beginning. The impact is very large at the beginning and is very small during construction. If the construction is happened, your influence is very small on the cost. So the impact is very big on the beginning. And if you're doing, let's say, a life cycle cost optimized design or a conventional design, you see that at the end of the lifetime, you have a huge amount of cost reduction. If you're doing a design at the beginning, it is advanced for the future. But the problem is, as I said, this cost till here is the investor. And the cost from here to here is the user. And this could be normally the same person. If you build a project for Google, if you do the headquarters for Google, then the investor and the user is the same. Perfect. It's a perfect project. But if you do a project for an investor and you're doing, and the user is totally different, unknown, then you have a problem with this thinking. But on the end, the whole society will pay. On the end, it doesn't matter who is the user or not. The whole society pays. We all pay the money for everything. So it means we have to look also on the cost over the lifetime of the building. And this is, I know this is not easy in the design process to bring it in the brain of the investor. So when we're doing design and we are looking for different variation of solutions, and the very simple equation is that the total cost is the capital cost plus the operational cost. And the operational cost is energy, maintenance, facility management. You need people who are running the project. So this is the operational cost. It's a very simple equation. And I give you and this capital cost, you have to take the annuity of this capital. When you go to the bank, borrow this money, you pay interest rate, and you have a loan over a certain time. This is the annuity. And this annuity gives you a yearly capital cost, but you have to pay for the loan which you take from the bank. And this total cost is, maybe show you one example here. This is a typical example what we're doing in the beginning of a so-called integral design process. We compare here three options. And you see these three options, they are quite different part of capital cost, maintenance cost, and energy cost. This option here shows is high capital cost. This option here is very low capital cost. But this option have high maintenance and running cost, and this option have less running cost. Small energy cost per year. This is the amount of money, euro, dollar, baht, per year what you have to spend for the project. Capital cost, maintenance cost, energy cost, facility management cost. So what you see when we're starting at the beginning, we have to, our client give us the task to compare. This doesn't matter what options these are, but we compare different options. You can have options for different facade, double facade, single facade, shading, without shading. And this cost you could compare by capital cost, by running cost, by maintenance cost. And this is what we're understanding about. You can also say life cycle cost, total cost, doesn't matter, it's the same approach. This is what I would like to tell your attention. Don't look only on investment and capital cost. This is only, and when you're looking on life cycle energy, means this is the life cycle of the building. And at the beginning, you have to build the building. This is to the year zero. To the year zero, you build the building. And to build the building, you need a lot of energy. When I look at this building here, you need a lot of energy for the concrete. You need a lot of energy for the glazing. You need a lot of energy for all this stuff here. Energy means to produce the product. The gray energy, we call it embedded energy or gray energy. And this is the embedded energy here. At the beginning, you have a certain amount of energy to build the building. Also the people who go to the construction, go with the car to the construction place, all the lifts, during construction, all this energy is included. So when you see what is a typical building, a typical building is you're using energy over the lifetime. On the end, you have such an amount of energy from the construction and from the operation. Depending what type of building you're building, is more energy efficient, less energy efficient. Or this is the, let's say, this is the King project. This building, what is this building doing? What is this building doing, this building? This building producing more energy on the building envelope as it needs for the operation. So we call it in Germany energy plus building. If you have a, how look this diagram for a zero energy building? What do you think, how look this diagram for a zero energy building? Zero energy building is, this is zero energy building. But I don't like this, because as an engineer, what is zero? Could you imagine that we can plan buildings zero? On the end of December, I adjusted, oh, now I have zero. Nearly zero. So, zero is for me a crazy approach. Zero is nothing. So you have maybe negative or positive, but zero, I don't know how the people will design buildings with zero. I don't know. Maybe you should ask them. But I don't know. So this is maybe you got it, this is over the time, you have a plus or a minus, and of course this is then the energy payback time in terms of economic. You have payback time of money, and here in energy we have payback time of energy. And this is of course, this is the great advantage, this is the great challenge. And so we built some buildings in Germany with this, energy plus, producing more as it consumed for everything in the house. For the household, for the heating, for the cooling, for everything. So this was a small, let's say, introduction in what is life cycle analysis, what is life cycle energy, looking not only by the construction, looking the whole time. Green means sustainable. I also don't like really open spoken green. What this means. This comes from the United States, doesn't matter, eco, green, I don't know. Maybe sustainable building or building according to certain sustainability. Maybe this is right word, but it doesn't matter, it's advertising, free, something like that. Yes, buildings need, as you mentioned, that building stock needs a lot of our total energy amount. In Germany, 40%. But we really have to fulfill the sustainability. It's not only energy. And energy is only a small part of all the sustainabilities. And in the next slide, you see there is a lot of other aspects. I would like to pay attention on indoor environment or outdoor. You can also say maybe outdoor environment quality. What is the quality outside of the building? What is the quality in our public spaces? We see a lot that go to Dubai. Do you think the people in Dubai like the outside spaces? The people in Dubai living in shopping malls. This is their life. Shopping malls, but outdoor quality of public spaces. This would be a nice challenge for urban planners to make nice urban spaces in Dubai, in the desert, to create public spaces where people like to sit, where people like to talk, but not only in artificial, I can hear that here, in artificial sounded air conditioning system. So this has to be our challenge. The challenge, the indoor and outdoor environment quality. There's another aspect, a lot of aspects. I took not from time of you knowing all these aspects, but I would like to attention. An integral design approach is more than energy. It's the whole picture of the building. And when you're looking on this indoor environment quality, I give you one example, one of our research. There was a question, how is the indoor environment quality affects the performance of students? Do we have, if we have better spaces, are the students maybe better power, better performance? Question mark, question mark. So this was a very interesting study over a long time. So we're observing a lot of students in classrooms. And we look at different indoor environment quality in these classrooms. And we check how concentrated they are, how often they're sleeping, how often they are concentrating, and so on. And this time was, by the way, these crazy machines there where all the students playing, you know, these crazy machines, you know, digital events machines, was not happened to this time. And so we had a nice influence only on the indoor environment quality. This is one of these pictures, and it shows you the following. It shows you that when the temperature is nearly 20 degrees, the students was the highest performance, is the students' performance. And it goes down if by higher temperature up to, as you see, 10%, 15% less students' performance. We measure that, by the way, by concentration tasks. They have to check every in the classroom, every people over 3-4 years. We have to check them over a long time. And also what you see in this diagram, if the air rate, means the air rate, how many airflow comes through these outlets. If a certain amount of air coming in the classroom, you see we can increase the performance of the students. And we are sure that we can use these results for also for office spaces, for our pride, for our working, because our working is not so simple like students checking the quality of performance. I don't know how you do it in your consulting office, but for students, we could say it's a very crucial point to have a good indoor performance. And by the way, this is much, much more important, like any low energy building. If you speak about low energy building, of course, this is also important. But this is much, much, much more important to see on the picture. If this is for a country, we can increase the student performance by good indoor quality. This is for the society dramatic, especially for Germany. We have not so much people. We need efficient people. This is one of the results. So by the way, when I'm very often in China, so this is the reason I go from here also to China tomorrow. And you see, in Germany we have the trend. We have, let's say, high comfort and high demand. But what we have to go, we keep the high comfort, of course, but we should build low efficient buildings, means low demand, means very high efficient buildings. This is our goal at the moment in Germany. Germany, the goal is we have high comfort in our office spaces, high comfort in the schools, but we have to reduce the energy consumption because we have no chance. This means Germany goes from here to here. And then you see what is in China. China, at the moment, they have low energy demand and low comfort. Because why? And when you go in a school in China, there is no cooling, there is no heating. The people go in there in the winter with big clothes and boots, and they have no heating, no cooling. Maybe a little bit lighting. So this means, of course, they have less comfort and they have no energy demand because they have nothing conditioned there. But this China would be going this way. China like to go low energy, keep low energy and go from low comfort, high comfort. But actually China going this way at the moment. This means China also, these people like comfort, but they do it with a crazy technology and very heavy air conditioning system in every spaces. And this means the energy exploding also in China. But this is the question, why they not do it, why they not doing this way? Because also the knowledge, the know-how of how to build buildings with low energy demand and high comfort. This is a lot of people there only doing copy and paste and build buildings like everywhere in the world. Crazy high buildings, nobody takes care of anything of energy or sustainability. But this is happening at the moment, the trend in China. So we will see how maybe they get this curve, and this curve turns maybe a little bit from here, back to there. This should be the so integral design approach, why are we doing that? As I was speaking before, we have a lot of, let's say, a lot of aspects. It's not only architecture, this is what you like, Arch. You like good architecture, right? Also, I like good architecture. But also, we have to look on the history of this place, this is what the architects doing. Materials, when I would like to build buildings from wood here in Thailand. Is wood available in Thailand? I don't see so much wood in Thailand. So the question is why we should build buildings from wood in Thailand. So if you go in Dubai, there is no wood. Why should we build buildings of wood? So this is what we have to thinking on our integral design. And of course, we starting with the urban, and we look on the urban design, and then we look in the architecture design. And I compare this integral design like similar with here with we have 3 guys sitting in this boat, and if they're not working together, they are a single approach. They are not know each other. They're working on the lake, but they have to be stronger, to be more efficient, to be more intelligent. If you build a group of people, and you have one guy who controls this group, and this guy have to influence all these guys in this boat. And I'm sure that this solution, that the people together, different disciplines, working together, is much more interesting and much more efficient. And of course, this information lag, what we have in this case, that this information between these 3 people is really weak. This information should be better because this guy should give the tact or the force. And we're working in the last years on this 3, 4, 5D modeling. We call it BIM is a process. It's not a software. BIM is a process where we bring these different informations on one platform together. This is, of course, this takes time. In big companies now we're using this building information modeling as a design approach on practical aspects. So one important things I would like to mention at the beginning is definition of aims and objectives. I learned in several of the projects we had at the beginning, we have to define the aim of the project. This seems trivial. This seems simple. But we have to define the aim of the project. And the aim of the project could be an energy efficient building, but could also be a building with a high comfort, or should be a building with low cost, or should be a building with, I don't know. The aim has to be clear. If the aim is not clear, then how we should in the team, let's say, solve this or come to this aim, what is defined maybe by the investor or maybe defined by the user. And also these people, the users, the investors, the facility manager have to be in this team to understand how to define this aim of the whole project. And maybe this is too detailed, but this is what we understand the value chain of integrated planning tools. We're starting with rough design concepts, and it's go more and more detail, more and more detail, and it comes to a call of tenders, it comes to a detailed planning, it comes to a detailed for the construction, very detailed design. Every piece is described, every piece is called for tenders, and then comes to the building process itself. Time management, cost management is included in this tool, in this step. Time and cost are in this step, and then comes to when the building is finished, the operation of the building. We should use the same software, the same platform, what we're using at the beginning, we're using for the operation. So this is what we understand under this integrated planning tool. And as I said, so we have this abbreviation BIM for it, Building Information Modeling. On the same platform, we're working from the beginning to the operation. And the values, I describe the values of integration. So typically, we're starting on a project, we analyze and define, as I said, we define the project, we define the aim of the project. Example here from China. And one of the next steps is that we define and discussing how the envelope should be. The envelope in Bangkok is quite different, like the envelope should be different like in Germany. Envelope of the building, the quality of the envelope. And so we are discussing about the architecture, the form of the building, as well as the envelope quality. What is the quality of the envelope? This is one of the most key points of our discussion of sustainable buildings. And if we have finished this discussion on envelope, we're looking on the technology, how we heat, cool, ventilating the building. And of course, also we have always consider the cost and the performance values of CO2 emission, cost per square meter, benchmarks for running costs. This is all this, the whole picture is this, we call it a holistic approach. Parallel, not sequential. A lot of people working step by step in this concept. This concept you have to work in the parallel time. And when the building is finished, and call it from the beginning to the monitoring or to the operation, you have always to check the quality control during the process from design as well as from the construction. I see a lot of different planning concepts where you as architect and engineer make the nice design, then the contractor overtakes the drawings, and the contractor do what he every time do. I don't know the typically planning design process in Thailand. But in Germany, we engineers, we keep attention from the first concept to when the building is handed over to the client. I know in China it's happened that the team are designing the building, make nice drawings, nice book, and then to give it to the contractor makes what he likes to do, what he likes to do every time. This is, you have no chance to check the quality of the building because they do it as they usually do. I don't know how it's in Thailand, it's interesting to get reflection from Thailand. How far are you in the project to check the quality? Check the quality during the process. So let's say you're thinking about concepts and about request of a building, depending on, of course, what is the use of the building. Between hospital and schools and office, there is so different requests and so different aims and objectives. To give you an example, in a hospital, you have very precise requests from temperature as well as from acoustic things. And a hospital works 24 hours, 7 days. But on an office building only 40 hours per week, maybe in Thailand 42, I don't know. But in Germany we work 40 hours, but normally it's maybe the building is used maybe 50 hours due to overlapping. In China, and actually in China, by the way, people working 70 to 80 hours per week. I have some got at the moment from China, and I asked them, why you come to Germany? They said, oh, Germany is green, Germany is a nice air, and you have no Überstunden. No Überstunden means additional time. Now in China, you have to work for the same salary, not 40 hours, 70 to 80 hours. So this is the reason they come to Germany. And so this difference of usage of a building, office, school, or hospital is very important at the beginning when you're designing your concept. There's a lot of ideas how to use natural resources, how to use natural, let's say, the daylight, natural ventilation. Give you one example. This is the European Central Bank. And when we're starting with the European Central Bank on thinking in the concept phase, we see this is the design, the first place from architect Norbert now. I have to check. Okay. This is the building, the European Central Bank in Frankfurt. And when we're starting, we first of all we thought what infrastructure is around. You see here there is a small river around. This is the mine called the Small River in Frankfurt. The building is in Frankfurt. There's a small river here. We have to see what infrastructure is here: district heating, electrical power. Maybe we can use the ground for cooling and heating, and geothermal sources for heating and cooling. And how the building is a huge high building. This means we have natural convection in the middle zone of the building. Maybe we say atrium, and this atrium working like a chimney, and this chimney will be held to support the mechanical or the ventilation of the building. So this is what we doing at the beginning, thinking what is there, use the ground, maybe using the ground because this high building using piles, and then basically maybe we can use these piles for energy, let's say, reasons. And the second way what we're looking is, this is by the way, this is the location. Here's a small river called Main, Frankfurt, and this is the building. And when we checking the location, then also we're checking what is around. Is there a lot of traffic? Is there a lot of railways around? Gives a lot of noise. So we have to think, what is with the noise there? How we protect the building from noise? And we're looking how the sun is running, let's say, over the building. So we have protection here, and maybe on the north, different like on the south. So ask you, have you checked? I mean, here different climate in Bangkok, but in Germany, 99% of all buildings have the same facade on north as on the south. Is this logical? Germany is quite different, like in Bangkok here, because we have summer, winter, we have the sun sometimes coming from 60 degrees, sometimes coming from 15 degrees. So, but it's not logical, isn't it? We have the same facade on north and on south. So this is what we are thinking when we're looking at such conditions around the building. And when we're starting such a concept, then we're looking first on the whole building concept. As I mentioned before, when we have an atrium, if we have some spaces here. Maybe we have office spaces, we have meeting spaces, we have different type of spaces in the building. So for every of these spaces, we have a different, let's say, concept. This means here, you can see that here. This is an office space with window for natural ventilation. Here, this is maybe a meeting area. We have a lot of people like here sitting together. We have a lot of exhaust heat. We need a lot of air in these meeting places, but in normal offices we have only 2 people. We don't need so much air exchange rates. So we're thinking on how the zoning of such a building is. We have a zone in the middle, we have some zones here, some zones are to the atrium, some zones to the outside. So this is a general approach for the whole building first, when we're thinking about it. Then we're discussing about the facades, how the facade should look like, for sun protection, for air infiltration, for opening, for ventilation. Maybe we have here a second layer for some infiltration or some reducing of acoustic noise, so that we can open the window and we avoid noise penetration. As remember, if we have railway closed, then we have to think on a we can say, okay, don't open the window. If you don't open the window, you have such a thing like here. But I would not like to work in such a thing like here, because this noise disturbs me in my office. Maybe here it's okay to be awake to the noise, but in my office I would not like such noise. And this is the reason we are looking for a different application. If we are discuss the facade with the architect, we come into what type of sun shading, what type of glazing, what type of shading we're using. Here's a shading device we're using many years ago. Also when Norbert speaks later on, we're discussing about shading devices who comes from down to the top, because here daylight comes in and shading is here, so we have enough daylight. But only when you have shading from the top, you'll be dark when you switch on the light. So this have to think on more intelligent shading devices, and also shading devices who are wind resistant for high buildings. If you have high buildings, what are people doing? They make the glazing dark, finish, sitting in the dark. This is not what we're thinking about. So we have to think on also shading devices. We have one in our case, in the 11th floor, is wind resistant, and you can do it also on higher buildings. On the side of the space itself, you see on the space itself, you're thinking on how this sun protection, how the cooling is, how the heating is, and this is you're looking on the space. I give you one example here. This is very famous in Germany, that you cool the slab, the concrete slab of tubes, and this we call it radiation cooling. Radiation cooling is very healthy because it's nothing moving air. For example, if you build a hospital, and you have to avoid all this air blowing dust around, and you have only cooling the ceiling. And this is a very hygienic and very interesting solution, especially for hospitals. When you cool the space for radiation cooling, you have here pipes in the concrete, like here you see that as a example how it works. Or here's some capillaries under the plaster. Or this is a traditional, maybe what you more knowing, cooling ceiling, where cold air flowing through the ceiling. Here in this room, it's air for the cooling. But we think this is not what we recommend for advanced building with, let's say, with high indoor environment quality. Maybe this is for combined with air exchange for fresh air, radiation cooling could be in some of the cases, not in all cases. In some of the cases, I think radiation cooling is also applicable in time. For investors, of course, you can, if you have not a suspended ceiling like here, normally suspended ceiling looks like, when you look at this design here, maybe we see that here. See that here? Maybe we have here 1.5 meter suspended ceiling. Here in this case makes not so big cool, but when when you build an office building with a lot of floors, floor, then you have to reduce the floor height is as more floors you can build in a certain height. So this means space efficiency or volume efficiency. And you see that in this case, when you not have a suspended ceiling, you can reduce your floor height of nearly 0.5 to 0.75 meter. And this means if you build a high building, like this is not a big high building, but it's a high building, and when you see if you avoid the suspended ceiling from here to here, you save maybe 4 floors more, and 3 to 4 floors more you can sell, you can rent to people. So this means if you avoid suspended ceiling, if you have ready cooling, you make a big business. A big business, and this is interesting for investors. Okay, I will skip daylight simulation and operational concepts. Also, you need an operational concept for in the beginning when you are still in the integral process. At the beginning, you have to think on operation. At the beginning, you have to think on operation. And how operate the building and who will operate the building. See, this is a nice picture. Maybe in the meantime, we have more modern screens. Do you think this is a monitoring or an observation of a facility management of a guy here? He's sitting in a room, in a space, in a big office building. You think, what is the problem with this? You have an idea what's the problem with this? The big problem is we have not enough experts to understand all these things on the screens. Most of the facility managers are sitting in the room and looking, is it clean, is it garbage well? And do you think we have enough people who can understand on screens? I mean, they're on security, they look for people around. But when we have a lot of diagrams and a lot of energy flows on the screens, what we need is we need experts. Experts. And the question for me is, do we have these experts? In Germany, we have not enough experts, by the way. We have 1.8 million buildings, commercial buildings, not residential, commercial buildings. 1.8 million. Maybe in Thailand you are similar. In China maybe you have 1.8 billion. Do you think we can observe all these nice things by people? I don't know. We need other solution. Maybe we have thinking. I will not give you the solution, but we should think. Thinking, do we have the people? So this is normally how to do facility management in the building. It's an interesting question. Do we have the experts? So now I shift to close to. I will before Mr. Himmler shows some project from Thailand here, what we have done recently. I mean, Thailand, you are quite happy. You are very stable in your temperature. You have Germany, you see we have a high fluctuation between winter and summer and winter again and maybe spring. Our year is really in fluctuation. You say you are always stable. It means for you this design of building is much easier because everything is stable. Every time you're hot and humid. We are a little bit different. We have cold, we have heat in the summer, also we have 35 degrees centigrade in the summer. So for us it's much more challenge to design a building like for you, because you are very, always hot and humid. But we have always going up and down. So this is one difference between you and us. Of course you have the same, you are the same people like we, so you also like it more in this range, but outside you have average this, and we have 9 degrees centigrade average. This is a challenge. And our difference from 8 degrees, and we have here this direction, we have nearly 12 to 10. So we have, I think I will skip that, but this is, you know, we have more heating problem, and you have more cooling humidification problem to come here in the comfort area. This is well known. And also one of the big differences in Thailand and in Germany, that your sun is always over your building. And this means when the sun is there, that the sun is always above you on your head. This is quite different to us, because you see in Germany we have, in winter we have this typically inclination, and in summer we have this inclination. And this of course must be an influence of the design of buildings. Yeah? And I will come to this. You see, this is what I teach in school. I also teaching not only weather data from Germany, also I speak about how to build a building in Thailand in our classrooms for the master. And so you see in the ground, you have always a hot ground here in Bangkok. Yeah? It's very hot. Nearly the typically average yearly temperature is only also 28. So your ground is very hot here. Yeah? Different in Germany is 10 degrees by the way. You are very hot here in the ground too. So, but you see, of course, you could be work with a, let's say, this ventilated double shell roof to protect you from your head, because your sun is always above you. And there's a lot of other features I would not like to mention details, it's lessons. But we will see that now in the real projects that we have considered this general approach of design approach for building. This is one building of my friend here, Elmar. I'd like to introduce him. He is an architect since more than 10 years. 30 years. 30 years in Bangkok, no, in Thailand. So 14 years, 30 years architect, I know, but he is 14 years active here in Thailand. So he is our knowledge base for all things happening in Thailand for architecture. So and he designed some years ago a headquarter of Hefele or Thailand, and this design center in Phuket. So he was not in my lessons, but he knows it because he's an expert too about how to design an office building or a design center in your climate. And he using this double shell roof over the whole block or over the whole building area, and he using let's say spaces, outdoor spaces with a lot of shading. Shading is important, and ventilation, natural ventilation by also using plants. Plants, you will see them in the pictures, and to improve the outdoor environment quality too. Here's a sketch of this project. It's at the DGNB level 4. Recently, we have done this in our office, and you see here the typically design of this roof with this zoning, different zoning of the building, and here this green area around the building. See here the cross section, now a long section of the building, and I think it's one of the first examples of going green and doing the right things in the right way by the materials as well as by the approach. Here you see Elmar told me these pictures he liked very much. You see in the roof also, it's not only a closed roof. The roof has some and you see here, this roof has some openings, some skylights, and this helps that the daylight in these office buildings are, of course, influenced by the skylights. And here the plants, the people sitting in these spaces, they have the feeling that they're sitting in the nature. And this is important. What I said, an outdoor environment is also very important, like the indoor environment. Okay, and now I would like to give the floor to Mr. Himmler. If we have, because it's a long lesson today, I have a lot of German projects, but I think when Mr. Himmler gives the Thai project, I would like to skip today the German projects, because you say maybe all these crazy German projects is another climate you cannot learn from. But this is the reason that Mr. Himmler shows you the really Thai projects, and maybe when you come into Germany, I show you the German projects. And this is maybe a good idea. We will see it. So I start the presentation, and then
Okay, so also from my side, a very warm welcome to this great event. I have to put the laptop in front of me. Is that possible? Yeah. Because I'm not really so much familiar with the presentation, because we actually decided yesterday evening that I give this presentation, so it's probably a bit bumpy times to times. Yeah, my name is Norbert. I am a German mechanical engineer. I'm in Thailand since around 2 years, and I work for the Joint Graduate School for Energy and Environment. I'm doing research on energy efficient buildings, and as Dr. Searing mentioned, we are currently developing a new Master for Sustainable Design together with the School of Architecture of KUTT, and since 6 months I'm Managing Director of EGS Plant Bangkok, so I also know a little bit about the practical side of design of buildings, and yeah, today I would like to introduce one of our two of our projects that we are currently designing. And yeah, I would like to start with a green factory. Unfortunately, I'm not allowed to give you the name of the company, because we signed a very strict disclosure agreement. It's a green factory in the northern part of Thailand, and the design, by the way, is also from Elma. It's really great and also sustainable. The client is very much aware about sustainability and energy efficiency, so the task for us was to create this kind of green and sustainable factory. The factory building itself is the big building at the northern part with a square meter of 19,000 square meter. Then we have additionally 6 administration and office buildings with a total of 11,000 square meter. So quite a big project. Then we have a halo, which is actually hovering above buildings and connecting the buildings, so it gives shade and also protects from the rain, so people can easily go from one building to the other. Yeah, the project team consists of OIA on the architectural side. OIA is a German architecture company which is based in Pattaya, and the energy concept is designed by EGS Plant, and we are closely cooperating with a big Thai engineering company, CRH, and they are doing the detailed design. As it was already mentioned by Professor Fisch, it's very important to do quality control throughout the whole design and construction phase. So this is what we are doing. So we do quality management during detailed design, tendering, commissioning of the building, and also during the first year of operation. And we do this within the framework of a LEED certification. Now, when we design buildings, the building envelope is a very important part for us. However, in the factory building, I have to admit that we have a lot of internal heat gains from processes. Nonetheless, I think we created a good and high quality building envelope consisting of 7.5 centimeter of thermal insulation in the roof. Additionally, we have some reflective paint to reduce the solar heat gains to the roof. We have glazing with a solar heat gain coefficient of less than 50%, but still we are getting a lot of daylight into the building to reduce the energy demand for electric lighting, and also when it comes to the wall, we have this kind of special bricks which have low heat conductivity. Much more important in that project was the ventilation concept. So what you see here is a sectional drawing of the existing company, the existing factory here in Bangkok, and you can see that we have huge huge amount of exhaust air which has to be removed from the building because we have harmful substances in the air from soldering, and we also have a lot of dust from grinding and polishing processes. And in the existing factory, they are only blowing out this actually conditioned air, cool and dry air out into the ambience, and that costs a lot of energy. So what we are doing in the new factory is we are cleaning the air by using active coal filters and by these dust collectors, and then we are returning back the air into the building, so we are not losing too much cold and dehumidified air. However, you must know that we have a total of 3,500 workers in that factory, so we need a lot of fresh air to keep them healthy. And therefore, we have designed a fresh air ventilation system. And that fresh air ventilation system has a so-called energy recovery wheel, which reduces the ventilation energy demand by around 80%. So it's not only transferring cooling energy to the supplier, but also pre-dries supply air. So very efficient system in comparison to the old factory. Yeah, this is the energy supply concept of the factory. We have a centralized chiller plant with a very high efficiency, with a COP value of 6.2. The cold water is distributed by district cooling system on the site, and then additionally we have as an energy source photovoltaic system with power of 1 megawatt. The problem currently in Thailand is that we don't have a feed-in tariff, which means you cannot produce more electricity than you need on site, and therefore we had to design the PV system so that it never produces more electricity than the factory consumes. So what you see here is the load curve of the existing factory, and we scaled this up to the size of the new factory, and then we deducted some energy savings, and so we found out that a PV system with an electric output of 1 megawatt will always supply less energy than the factory actually needs. Yeah, this is the projected energy balance of the building. On the left-hand side, you can see the energy demand of the existing factory. On the right-hand side, the new factory. And if we take into account the energy produced by the photovoltaic system, we can achieve energy savings of up to 40% in comparison to the existing factory. But as Professor Fisch already mentioned in his presentation, energy is not everything. We developed a whole holistic sustainability concept, and for this we were using green certification, where we are not only taking into account electric energy demand, but also the comfort, the built environment, the materials, the sustainable site, and also the water efficiency. And at the moment, we are anticipating a LEED Silver level, which is quite ambitious in the factory. Yeah, so this is our goal for the project. Yeah, that was the first project. It's a really big project. Now I would like to introduce a very small project, but nonetheless super interesting and super ambitious project. It's a single-family house for Thailand's biggest real estate developer, Buxa. And the idea of this project was to design a single-family house which fulfills the highest sustainability and energy requirements. So how did we achieve this? First, in the first step, we are reducing the cooling energy demand of the building by applying passive measures, like for example shading and thermal insulation. And then we are covering about 90% of the total energy demand with renewable energy. So it's almost an energy self-sufficient building. And finally, we will certify the building according to the German DGNB certification system, which is from our point of view, the better system also in comparison to LEED, because it's more holistic and it's more detailed. Yeah, the current status of the project is that the piling is in the process and the building will be finished end of 2016. So what you see here is the concept of the building envelope. You can see that we have a very good thermal insulation of 10 centimeter in the roof. We have 5 centimeter of internal thermal insulation. We are using high performance glazing with a U value of 1.1. So this is about 5 times better than the normal glazing that we are using in Thailand. We have external shading, not only in the area of the window, but also the shading also protects the wall to reduce the solar heat gains through the wall. Also the roof is back ventilated, which also reduces the cooling load in the building. So we are not only designing the rough overall building envelope, we also really go into detail, because in most projects where people are applying thermal insulation, they probably put the insulation until here, and then you have a gap between the window frame and the thermal insulation, and through this gap you are losing a lot of thermal energy. So what we are doing in our project is we are trying to cover the window frame as far as possible with thermal insulation to reduce this thermal bridge. And another thing we are taking into account is reducing the air leakage of warm and humid air into the building, so developing an airtightness concept. So what we do, for example, is we connect the concrete wall and the window frame with the construction tape, so no hot and humid air comes into the building. But again, there are people living in this building, and therefore we need fresh air, and therefore we have developed a special ventilation concept. In that building we are using a decentralized ventilation system consisting of these small ventilators which are integrated in the wall. We have for each room, we have 2 of these systems. So we have 2 ventilators in each room, and to achieve the energy recovery, because the disadvantage of decentralized ventilation systems is usually that they are cheap and easy to handle, but you don't have an energy recovery, because for this you need actually to have the fresh air and the exhaust air close by, so usually you can only do this in centralized ventilation system. But here we have a special heat recovery, it's the yellow part that you see here, and this acts as a regenerative heat recovery, and this is how it works. So what you see here is, for example, one room in the building. This is the outside, this is the outside, and one ventilator supplies the fresh air from outside into the building. It is cooled down in the heat recovery. The heat recovery itself consists of a ceramic material. It acts as a thermal storage, and therefore it cools down the air. At the same time, we have here this exhaust ventilator. And in this case, the heat storage, the ceramic, is loaded with cooling energy. And after around 70 seconds, the left thermal storage is empty, so the supply air is increased here. However, on the right-hand side, the second storage is almost filled with cooling energy. And after 70 seconds, the whole airflow is turned around. And by this ceramic heat storage, we achieve heat recovery rate of up to 90%. What you see here is the energy supply concept. So there is a little story behind it, because we originally planned this building as an energy plus building, as Professor Fisch showed in his presentation, a building which produces more renewable energy than it needs for operation, and then the idea was to sell this electric energy to the public grid. The problem is that since June this year, there is no feed-in tariff possible, and it's actually even forbidden to feed in somehow have to store it for nighttime, because actually in a residential building you will have the highest energy demand during nighttime due to the air conditioning, which is normally running during nighttime, and also because you have the household appliances and the lighting during the daytime. There's not so much energy demand because usually the family are at work or in school. So the first idea was to have a big battery to store the electric energy. Now the battery has a couple of disadvantages. First, it's very expensive. Second, you have to exchange it every 2 to 3 years. You know it from your mobile phones. And third, the battery is made of lead, so that's also quite a harmful substance to nature. And therefore, we were thinking for alternatives. So we thought actually most of the energy that we need during nighttime is thermal energy. And so we thought, okay, maybe we can just store cold water in a cold water storage and then supply it to the air conditioner. So we made a rough calculation and we found out that the cold water storage would have a size of 8 cubic meters, 7 to 8 cubic meters. So we thought, wow, that's a little bit big for a single family house. So we decided to go for ice storage, because an ice storage can store much more thermal energy due to the phase change which is taking place. So what we are doing now in that building is during daytime we produce a lot of electric energy from the PV field. We supply it to the battery, we charge the battery. We are at the same time running the chiller. The chiller produces ice for the storage. At the same time it also produces hot water, which is stored in the domestic hot water storage, so we can use it later in the bathroom for taking a hot shower. And during nighttime, when we don't have any solar energy, we are discharging the battery, run the household appliances. We can switch off the chiller and discharge the ice storage. So I think this is a quite unique energy concept, and therefore we have to apply thermal building simulation. So what you see here is 1 week of thermal simulation in April when there is not a lot of solar radiation. So this is actually the worst week that we could find in our simulation. So what you see here, the red line, is the energy demand in the building. The big peak during lunchtime is the electric energy demand for the chiller. The green curve here is the photovoltaic energy. And the area which is between the two curves is actually the energy that we can supply to the battery. And at the same time we are charging, it's the blue curve here, we are charging the cold water storage. And it's quite interesting to see on Thursday, Friday, Saturday, and especially on Sunday, you can see that the solar radiation is getting less. And therefore we don't have enough energy in the battery anymore. That's the reason why we have to still get some energy from the public grid. Yeah, in this diagram we can see the annual energy balance of the building. The left column shows the energy demand. The red area is the energy demand for household appliances. The blue area is the energy demand for air conditioning. And the next column shows where the energy comes from. The green area is the electric energy which is directly supplied from the PV system. The violet area is the energy which comes from the battery discharge. And then we need the additional energy from the grid. And the orange part is the energy that we are actually producing too much in the building. And the goal of our optimization of the size of the ice storage and the battery, and also the size of the PV field, was to keep these two areas as small as possible. I mean, if you come to the violet area on the same height as the energy demand, then you have a self-sustainable building, but that doesn't make sense from the point of economics, because then you have a very big battery system, big ice storage, and a big PV system, and this we want to avoid. Yeah, I also calculated roughly the annual energy costs in the building. So the energy costs are around 2,500 Thai baht per year. So this is my electric bill per month. So it's really energy efficient. As Professor Fisch already pointed out, monitoring is extremely important, especially if you have such an ambitious energy concept. So what you see here is the technical implementation, and the yellow dots is the measurement concept. We have a weather station, for example. We have temperature and humidity sensors in each permanently used room. And we have a lot of temperature sensors, of course, in the technical room to monitor performance, the overall performance of the system. We have electric meters integrated in the PV system, in the battery, and also how much energy does come from the public grid. We have meters to measure the electric input into the chiller and the cooling energy output, so we can calculate the performance of the chiller, because that's quite crucial. You have to imagine that the supply water temperature here is -5 degrees centigrade, which means that normal chillers would have a very bad performance. But fortunately, we can use a German heat pump, which is modified, and we can achieve a COP of up to 3.2. So this is what was promised by the factory, by the company. Yeah, that was already the last slide. Thank you for your attention. I hope I could show you how we could apply. Actually, I didn't talk too much about the design process in both projects. And actually, we were applying this German strategy of having the integrated design approach. So we met really very often with the design team to achieve a good goal. And yeah, so I think that's the message from my side. Thank you.
To perhaps summary what we have learned today, before we thank you for the speaker. Okay, อาจารย์ครับ
สวัสดีครับเขาให้ผมซัมมารีในภาษาไทยนะครับเพราะว่าเป็นนักเรียนหลายคนนะครับก็ต้องบอกว่าซัมมารียากเหมือนกันเพราะเนื้อหาหลากหลายมากในวันนี้นะครับตั้งแต่ต้นมาว่าผมเป็นตัวฟิชเนี่ยพยายามพูดถึงเรื่องความสำคัญของไลฟ์ไซเคิลกับไลฟ์ไซเคิลแอนาลิซิสนะครับของการออกแบบอาคารที่เราต้องมองเรื่องของ capital cost แล้วก็ operation cost นะครับซึ่งเป็นสิ่งที่ท่านก็บอกว่ายากไม่ว่าที่ไหนก็มีปัญหาหมดนะครับเรื่องการมอง capital cost มาสำคัญก่อนนะครับแล้วก็พูดถึงเรื่องแนวคิดในการออกแบบหลายๆอย่างนะครับก็จดมาบ้างนะครับต้องเริ่มจากไอเดียในการที่จะทำให้เกิดการทำประหยัดพลังงานแล้วไอเดียนั้นมันกำหนดเป็นดีไซน์ออกมาได้อย่างไรนะครับแล้วก็ไปถึงเรื่องของการก่อสร้างเรื่องของคอมมิชชั่นนิ่งนะครับท่านเน้นว่าคอมมิชชั่นนิ่งก็คือว่าจะทำยังไงที่ทำให้พวกแบบนี้สามารถกลับไปการันตีกลับไปเช็คได้ว่าเนี่ยคือฟอร์แมตของอาคารเนี่ยมันเป็นไปตามที่เขาออกแบบจริงไหมนะครับซึ่งอันนี้เป็นสิ่งที่มีปัญหามากในประเทศไทยเพราะว่าเราก็จะไม่ได้ค่อยไปดูฟอร์แมตอาคารจริงจากที่ตั้งแล้วว่าเราคิดยังไงครับนั่นก็คือสิ่งที่สำคัญมากว่าท่านก็บอกว่าเรื่องของ capital cost จริงๆแล้วมันเป็นแค่ประมาณ 10-20% ของคอสของอาคารตลอดการใช้งานบางครั้งเราไปพุ่งเป้าที่เรื่องของ capital cost มากจนเราไม่ได้สนใจ operation cost อีก 30 ปีของอาคารที่มัน 80% ของคอสทั้งหมดนะครับนั่นก็เลยคอนเซ็ปต์ว่าเราจะต้องเอาคอสทั้งหมดเนี่ยลองมาคำนวณเป็นรายปีอยู่30 ปีหรือว่าเป็นค่า annual cost แล้วเปรียบเทียบกันเลยของแต่ละออปชั่นว่าอันไหนเนี่ยเป็นสิ่งที่เราควรจะให้ความสำคัญมากกันนะครับก็น่าจะให้โชว์เรื่องของคอนเซ็ปต์ของอาคารที่ว่า Energy Plus นะครับซึ่งก็เรียกว่าเป็นสิ่งที่สำคัญมากนะครับว่าวันนี้เราสร้างอาคารเราใช้พลังงานไปแล้วนะครับดังนั้นวันข้างหน้าจะทำยังไงให้อาคารนี้มันผลิตพลังงานมันชดเชยที่มันใช้ไปนะครับนี่คือคอนเซ็ปต์ของ Energy Plus ที่มากกว่าเรื่องของ Zero Energy Living นะครับแล้วก็สิ่งต่อมาที่ท่านให้ความสำคัญนั่นคือคำว่า Integrated Design หรือ Integral Design หรืออะไรก็แล้วแต่นะครับคือมันการออกแบบหรือว่ามีส่วนร่วมกันระหว่างหลายกลุ่มก็คือทุกคนนักสถาปนิกวิศวกร Facility Manager ต้องมาร่วมกันแล้วก็กำหนดว่า aim ก็คือเป้าประสงค์ของอาค คารต้องการให้เป็นอย่างไรแล้วแต่ละคนมีส่วนในการทำงานได้อย่างไรบ้างนั่นคือสิ่งที่ท่านเน้นนะครับเรื่องของ integrated design ซึ่งก็เป็นสิ่งที่ไม่ได้เกิดขึ้นได้ง่ายนักเพราะว่าเรื่องของการออกแบบบางทีเราก็ยังไม่ได้มีทีมงานชัดเจนมากนะว่าฝ่ายเป็นใครบ้างนะครับก็แล้วหลังๆมาท่านก็พูดถึงเรื่องของอาคารนะครับเคสที่ของอาคารซึ่งเราอาจจะไม่ค่อยเห็นภาพชัดมากนะครับคือเทคนิคที่มาเสนอมากคือเรื่องของคอนกรีตคอร์ลิกนะครับซึ่งพูดถึงว่าอาคารสูงเนี่ยจะเซฟพื้นที่ไปได้หลายด้านชี้หรือว่าเรามีเพดานที่เราใส่ท่อลมไว้เยอะมากนะครับลองนึกภาพดูถ้าตึกมันเป็น100 ชั้น200 ชั้น100 กว่าชั้นที่เราขึ้นในประเทศไทยเนี่ยเราจะเสียพื้นที่เสียวอลลุ่มตลอดที่ท่อลมเนี่ยเป็นร้อยเมตรเป็นเงินอีกเท่าไหร่นะครับตรงนี้ก็เลยว่าถ้ามันมีเทคนิคใหม่ๆขึ้นมาเรื่องคอนกรีตคอร์คูลิ่งมันอาจจะมีความคุ้มค่าก็ได้ครับก็นั่นคือสิ่งที่เสนอนะครับหลายส่วนที่มาผมก็อยากได้ประมาณเท่านี้นะครับก็คือสรุปว่าก็จริงๆแล้วท่านก็อยากเสนอเรื่องความแตกต่างนะครับและความเหมือนระหว่างที่เรามากันครับมันมีบางอย่างที่มันแตกต่างกันมีที่เหมือนกันนะครับแต่ว่าเราจะอัดแอปได้ยังไงนั่นคือท่านเสนอการเรียนการสอนที่สถาปนิกวิศวกรเนี่ยจะต้องมานั่งเรียนด้วยกันนะครับในหลักสูตรที่ท่านกำลังเสนอขึ้นมาคือเรียนด้วยกันนะครับมันจะมีวิศวกรนะครับผมคิดว่าผมก็คงจะ summary อะไรเท่านี้พอจะสรุปได้นิดหน่อยนะครับก็ท่านคงจะมี